Hi guys, Mr. T here. Today we're going to be talking about graphing cubic functions. That's the beginning of Module 3, Section 1 of our new textbook. We're getting into polynomials. We've been talking about quadratics, so just x squared with nice little parabolas going on. But now we're going to move into polynomials. And the first one we're going to look at is a cubic, which is very, very similar. And we're going to be looking about how this vertex form is basically the same idea. And so if you'll look at here, essential questions, how the graphs of these guys related to the parent function with this x cubed. But if you'll notice, they're just like it was with squares, except it's got a 3 here now. So it's all the stuff we knew before is still there. The shape's just a little bit different. So let's talk about that first thing. We're going to do that, and then we're going to talk about these attributes. And then we're going to do some little practice things and how that looks like, okay? All right, so let's jump on over here. Look at this guy here. So let's back up just a little bit. Let's back up just a little bit, and let's start off with looking at what we already been doing with a quadratic, okay? So y equals x squared. So this is a quadratic function, a quadratic equation, and you know it's a quadratic because its highest exponent is 2, okay? And so that's what that is. Its picture is going to be a parabola, right? That's what it's going to do. And so what we're going to do is we're going to just take a table, x and then y, and we're going to plug some numbers in, okay? So if I plug a 0, I get 0, 1, 1, 2. 2 squared would be 4, and so on. So how about some negatives? How about negative 1? Negative 1 would be 1. Negative 2 squared would be positive 4. And so that's what we're going to do here. I'm just going to plot these points over here. So let's start with 0, 0. Boom. All right, then 1, 1. Over, say if we go 2 squared is 4. 3 squared would be 9. 4 squared would be 16. 5 squared would be 25, way up there, okay? Okay, now let's do negative 1. Negative 1, okay, negative 1. I'm sorry, negative 1, positive 1 squared. Negative 2 squared is positive 4. Negative 3 is positive 9. And then negative 4 squared would be positive 16. Because when you square those negatives, they turn them all back to positives. So let's connect the dots. So this is what we'd have for my parabola. Trying to make it look at least decent here. Did better on the right hand side and the left. All right, so there's that. Okay, so that's a parabola. So what's the difference it's going to make when we go into doing a cubic? Well, and again, this is the parent function. I don't know if I mentioned that previously. And it's the parent function because there's no up and down, there's no left and right, there's no flipping. It's just the basic one. So the parent function, when it comes to the cubic, is very, very similar. It's just going to be y equals x cubed, thus the cubic. Okay, and it's going to look very, very similar. So this is a cubic function, a cubic equation, because its highest exponent is 3. Okay, and it's going to look very, very similar to the parabola, but a little bit differently. But before we do that, let's just get a few little points running here. So the calculator does a lot of this for us, but I just want to reinforce where this is coming from. So 0 cubed is still 0. What about 1 cubed? 1 times 1 times 1 is still 1. All right. How about 2? 2 times 2 is 4. Times 2 is 8. And then 3. 3 times 3 is 9. And 3 times 9 is 27. Okay. Come down here a little bit more. So let's do some negatives. How about negative 1? Well, if that was a parabola, we would just say that's positive 1, right? Well, negative 1 times negative 1 is positive 1. True. But then positive 1 times negative 1 gets back to negative 1. So that's a little different when it comes to cubics. You're not always, you can get negatives coming out. How about negative 2 cubed? Well, negative 2 times negative 2 is positive 4. Okay, whoops, go this way. Positive 4. And then positive 4 times negative 2 is going to give you negative 8. So it's a little bit different, isn't it? Okay, so let's go back up here and actually do some graph some of these points and take a look at how that looks different. So 0, 0 is the same. 1, 1 is the same, but it's not 2, 4. Now it's 2, 8. And you should get familiar with the cubes, at least through 5. You know, 1 cube, 2 cube, 3 cube, 4 cube, and 5 cube. Those are used a lot. So I suggest you get familiar with those. So let's 3 cube, 27. Can't really do that. But I'm just gonna like stick a little dot up there somewhere. Give us an idea. Because what we can't do is actually hit the 3, because it doesn't hit the 3 till way up there, does it? So I'll put a little dot right there between them. So that tells me not to do that. So here we go. We got -1, -1. -2 cubed is going to give me -8. And then -3 again is going to give me -27. Way down there somewhere, right? So it gives you that right there. Somewhere along that lines. Just plain connect the dot. Go up, there it is. Not the most beautiful, but we're giving it our best shot. Okay. All right. Now, first thing you might want to notice, other than the curvy lines, is that this is more narrow, isn't it? Well, let's think about it, because it started off the same, but this next one jumped much further up, and the next one jumps way further up. So it's rising way faster than the other one. So it starts off more narrow than the other. Okay. But it's still a very similar shape. But look, the left-hand side of the parabola basically has gotten turned over and down, because we can't have negatives. With the squares, everything negative turned back to positive. But since you have a cubic, you can have a negative y. And so that's what's going on with this. And so this is the parent function for the cubic. Okay. So they're very, very similar. Okay. Very similar, but it's got an odd, and we call this a positive slope as well, because if it kind of runs like if you drew a line from one end to the other, it would be a positive slope. Okay. That's just a comparison between these two parent functions. So make sure we're getting that vocabulary straight. So let's look at some notes in our book here. Okay. If I can get to the right spot, that would be good. Let's go to this one over here. All right, this one's already filled in. That's all right. And so here in our current textbook, I guess this is page 235. They start off with just doing like we did, getting some ordered pairs and plotting the points. And so this is the parent function for the cubic parent function. Okay, and so that's kind of what that looks like. You should try to familiarize yourself with that. So now let's talk about its attributes. Okay. Well, I said the domain is all reals because it goes from left to right forever. There's no limitation on it. Okay. And the range is kind of the same way. But is there another way we could write those? Yeah, we could write those differently. We could say those, we put that or. We could say that's negative infinity, comma, positive infinity. Right? It's the same thing. It's the same thing. So those can be written in that way. All right. And then as x approaches, so what is that saying? As you go to the right, it's going to go, y is going to go up. So as we go to the right, it's going up. And then the other says as x approaches negative infinity, y's are going down. So as you're going left, the y's are going to go down. Again, for the parent function, the cubic parent function. The zeros are just x equals 0 because that's where it crosses the x-axis. Okay. The next part of it to take note of is the function values. What's it saying? Where are the y values? The y values are positive when the x is bigger than 0. So basically, over here to the right of the origin is where all the y values are positive for the parent function. And the second one says where's the function negative, right? So where are the y values negative? Well, to the less than 0, right? Why not equal to? Well, we already got the equal to. That's 0. It's not positive or negative. Okay, and so then we keep on coming down and start talking about it. It says, where is the function increasing? And it says the function increases throughout the domain. So let's go back up here and take a look at that. How about increasing? That means it's a direction of travel. So as you come from the left and move to the right, it's going to be going uphill the entire time. Now, sometimes the y's will be negative, sometimes the y's will be positive, but it's going to be going uphill the entire process, okay? And don't let this arrow down here throw you off. This is not a direct, this is just telling you that goes on forever. Doesn't mean it always goes this direction, because then it'd be confused because it's going down this way or up that way. Now, what we're talking about is going from left to right, from way over here in negative infinity all the way over. It's always going up. So if it's always going increasing, the y values are always increasing, then when's it decreasing? Well, never. Okay, well, never. It's never decreasing. So that's the next thing it says. The next thing talks about odd and even function. Now, this can be kind of confusing, okay? Because our main thing when we're talking about polynomials is whether or not the degree, which is the highest exponent, is odd or even. That tells us a whole lot about what it does and its behaviors. But this is saying not the degree of the function. It's talking about is it qualified as an odd or even. And previously we talked about an even function. Basically, if you take it like this and flip it, do you get back the same thing? And that's fine as long as you stay on the y-axis. You can move it up and down, you're good. An odd function, we said if you can turn it around 180 degrees and get back what you started, that's an odd function. And this is how they write that in function notation down here. And so this is an odd odd function, because this works out just fine. All right, isn't that nice? So here we go. Always changes you make. So those are some of the attributes, and you'll have some of that in your homework where they're going to be asking you about those attributes. Okay, so where did the rest of this go? Let's go. Let's do it that way. Woo. It's not wanting to show up. Okay, go here, come back. Maybe it'll behave itself. Nope, that's all right. We'll just come over here. Shrink it up a little bit so we can move. So we've already talked about those things right there. That's its attributes. So what the book likes to do is it likes to take a look at this stuff and look at some reference points. Okay, see where it says here, the reference points. Here. These guys, it likes these guys right here, reference points. And so these are the reference points on the parent function. And if we can track where these three things go, we can get a good idea of what's going to happen to our translated function. That's kind of weird. Kind of a little shadow there. Let's put that right over here then, okay? All right, and so they said, let's take these 3 points and see what happens when you put them through this translated function, okay? So, but that's nice. It's not a real big deal to me. I just rather you remember what we've already talked about. As you look at a number, you got to ask yourself, is it on the inside of the parentheses or on the outside? Anything on the inside, that's X's world, and X's go left and right. Okay, anything on the outside, that's Y's world because they go up and down. Okay, whether that means they're shifting left and right or up and down, or if they're stretching or compressing left or right and up and down. Okay, but those are idea. If it's inside, it's going left and right. Okay, and it's usually opposite because our formula said what? Negative H. Okay, it's always the opposite of what it seems on the inside. Okay, so let's just look at this. I like going from right to left with these guys. So this -1 right here is on the outside, and so it means up and down. It means it's going to go. So from the parent function, it's going to go down 1 unit. So let's just track this vertex. Which, by the way, we haven't mentioned this previously. Yes, we kind of call this the vertex, but it's really, that's just kind of what we call it. But what it really is, okay, is the point of inflection. Inflection. Oh, I didn't think I misspelled it. I think inflection. There we go. Probably misspelled it, but the idea is point of inflection. All right. That's what it actually is, but it works the same way as a vertex would with a parabola or an absolute value graph. Okay. But it's actually called the point of inflection. Okay. So what happened? This guy went down 1. See this point right here? It's down 1 from the other. And then let's talk about this one. Okay. So it's on the inside. That means it's going to be shifting left or right. So -1 makes me think left, but I know inside it's always backwards because of the formula. So that's not left 1, but right 1. So it went down 1, right 1, just like it was supposed to. Now, what about this A? That's what does the stretching or shrinking. Okay. And so we see this is a stretch by a factor of 2. So remember, that's over 1, right? So it's rising faster. Okay. So if I take my little semi-cubic shape thing here, and if I stretch it, that means it's getting taller, right? And skinnier. Okay. If I compress it vertically, it's going to get wider, right? It's going to get wider. So as long as the rise is bigger, it's getting taller and skinnier. Okay. When the run of the rise over run gets bigger, that means it's getting wider. Okay. So that means it'll be a vertical compression, pushing it down, making it wider. So that's what's happening with this guy. And you can kind of see it, the action happening here. Because look what the deal is. You go up 2 over 1. See that? See that rise over run thing? Over 2. Up 2 over 1. See how that works? And so you can use these 3 points here to do a pretty good job of either doing a quick sketch, pretty accurate sketch, or if you have the picture, to use that and turn it into the equation itself. We'll do that in just a moment. So let's slide on down, look at a couple more things. This one's a little bit different. It has a horizontal issue in here that is not so bad. So before we do that, let's review the deal here. The very top. This is our vertex form. So we got the A, that's the outside vertical. Now we got this B, it's on the inside. You notice it's 1 over B because again, the things on the inside seem to go backwards. So that's a reciprocal. Seems to go backwards because that everything's backwards inside there. At least it appears to be to us. So let's get them back here. Okay. So what is going to happen to this guy here? Well, this +4 still going to make it go up 4. So our vertex is going to end up, okay, again, get my whole picture on top of myself here. So I know that my vertex is going to go up 4. I know that's going to happen. Okay, I know it's going to have to go up 4. And then this 3, what's going to happen to the 3? Well, it's on the inside, and it looks like it's going to go to the right. But remember, on the inside, it's backwards what you think. So it's going to go left 3. And that's where my new vertex is going to land. That's where my new vertex is going to land. Now, are these other 2 points going to still just be 1 over and up 1? No, because why? We have this 2 thing going on, don't we? We have this 2 thing. So it ends up going a little bit different. Okay, and it says a horizontal compression by a factor of 1/2. So factor of 1/2. Now, how did that get 1/2? Because this number ends up being 1 over b, if you remember. So is that going to make it, so it's horizontal stretch or compression. So let's think about this. It's kind of harder to do this with my little guy here, okay? So if I'm going to, if I take this cubic here and I compress it horizontally, that makes it taller, right? So when it's on the inside and the rise is bigger, that's called a horizontal compression. Okay, if I stretch it horizontally, it's getting wider. It's getting wider. So that means the run would be bigger, right? So this is 2. So this one should be getting skinnier, right? Thinner. So how can I make this guy skinnier by doing horizontal things? That would be a horizontal compression would make it skinnier. Okay? Make it skinnier. So this guy should look up here. Kind of deal. You can always stick that in the calculator, take a double check on that. Ideas. Let's do it. Well, I'm not going to spend the time on that on the calculator because it's nice, and I want you to be able to do the horizontal, but I mostly want to challenge you with the horizontal so that you can easily do the vertical. Okay, because it's a good, but vertical takes care of most things. So let's talk about this guy. What's going to happen? Well, that's going to go right 3. What's the negative in front? The negative in front doesn't change its shape. It does what? What does the negative in front do? What's the negative on the line do? It flips it over. Doesn't necessarily change its shape, though. Now the 1/2 is going to change the shape, but the negative is only going to flip it over. It's called a vertical flip or a reflection across the x-axis. Okay, that'd be its official term. Reflection across the x-axis. So this guy's going to have a vertical flip because of the negative. Guess I can go ahead and write that. So let me circle this. So we'll call that a vertical flip. And go to green. That means it's, see, 1/2. So it's running more. So the way I'm going to make that happen is I do a vertical compression that'll make it run wider. Okay. So this is a vertical compression. Okay. And then I got this red. What's this 3 doing? It's going to go right 3. So that's what's going to happen with these guys over here. So it's going to go, the vertex is going to go right 3. Okay. And instead of going over right and up, it's going to go down. So, and it's going to go over 2 and down 1, 2, and then this way. And so this guy is going to look more like this. Okay, we'd have to get more points to know for sure where the other stuff goes. But these points would be a rough start to what it would in the transformation would look like. Let's look at a couple more of these. I'm going to skip this section right here for just a moment. Let's go on down to some more practice problems, okay? Okay, so this guy right here, this would be right 4. So it'll be a vertical, because it's taller, be vertical stretch. Okay, and then that part would be a vertical flip. Let's come on down here, because number 3 and number 5 are very similar. There's no vertical flipping going on, or horizontal flipping, because if it's on the inside, it's horizontal flip. All right. Then, and now this 3, so if it was on the outside, it would be a vertical stretch, just like it's 5, right? But since it's on the inside, this 3 is not going to be a vertical stretch. It's going to be a horizontal compression, because it's exactly opposite. Okay, now, and this one, this will just be, whoops, I'm about to say down. This would be up, because it's just straightforward up 2. Okay, that's what's going on there. Let me give you couple more real quickly here. Let's go back up to these guys now. That was a few of those. Let's do this in reverse. Let's do this in reverse. Okay, let's just look at this guy. So here is your vertex form, okay? And then here is our transformed graph, okay? So you need the A, you need your A, you need the H, and you need the K. Matter of fact, I should probably go back and change my H and K to different colors. There's my H, and then there's the K. How's that? So the H and K are real easy. So the vertex, or the point of inflection, is where you get your H and K. Easy enough. But how do you get your A value? How do you get the A value? Well, to get the A value, what we're going to do is we're going to go from the vertex up to our first little point there. And what is that? That's 3/1. So that is where they're getting this A equals 3 thing, is right here. From there to there. And so that's where the A is coming from. And I guess I can go ahead and highlight that. All right. So that is my A value. So you stick your 3 there, and then all of that turns in that. It's a very similar thing. So you can take that information and plug it in to get your equation, just in reverse. All right. So what we've been dealing with is we're just been graphing or some cubics right here, and it's like anything. At the worst comes to worst, just go ahead and put the thing in your calculator and plot a bunch of points. You'll get a good idea of what's going on. But we can be a little bit more savvy about it now, because we understand how the vertex form works. Graphing cubic functions. Have a good day, and hope that helps.